Hi and welcome to this Leaving Cert Applied Maths video. In this video, we're looking at work, energy and power. So in this video, we're going to explore the ideas of work, energy and power and how they link together in applied maths. So we're going to explore what energy is, how it can be transferred. We're going to look at the work done by forces, and we're also going to look at forces that do no work. We're going to use the conservation of energy. We're going to explore power and steady speed situations. So just to state that this video is suitable for both higher and ordinary level students, the work we're doing in this video will be more likely to, you will be more likely to meet this mixed in with other topics in exam questions. It's rare we see an exam question that works with just these ideas. I've linked some videos below where you can see work, energy and power linked in with other topics on our course. So let's talk about work. When a constant force acts on a body, the body moves and work is done by the force. And that work is given as work is equal to force times distance. So our S there for distance or displacement. That F represents either a force, it could be a component of a force, so maybe a part of a force, or a resultant of forces. So if there's multiple forces happening, that could be the case. And our S is our distance or displacement. So a few things to note. Work itself is scalar and its SI unit is the joule. But when you go into dimensional analysis, we're going to need to break that down further. And we're going to break that down as 1 Newton meter. The easiest way to see that is with that formula, work is equal to F times S. So F being force, which is measured in newtons, and S being our displacement or distance measured in meters. So work is a scalar, so it doesn't have direction, but we can have positive or negative work depending on the energy transfer. So that's really important to understand. It is scalar, okay? So work is scalar, but we can see positive and negative work. So positive work happens when energy is added to a system, okay? So think of us like stretching a spring or an elastic band or speeding up an object. And negative work happens when energy is taken out of a system. So imagine as a spring returns to its natural length or friction that's slowing an object down. So it's very hard to talk about work without talking about energy. So energy is a physical quantity that measures the body's ability to cause motion or change, or basically energy is the ability to do. Okay, so for us, energy and work are very, very strongly interlinked, and it's very hard to do one without the other. So, energy, just like work, is a scalar quantity. And some objects have energy because of their position. And we think of this as potential energy. So, for example, if you hold a stone 10 meters above the ground, the potential energy will be equal to mass times gravity. So, its weight times that height above the ground, that 10 meters above the ground. But that's called gravitational potential energy. And there are other potential energies that we will meet in our course. So other objects may have energy due to their speed. So we call that kinetic energy. So kinetic means movement. So for example, a car moving at 30 meters per second, even if the engine is off, it does have kinetic energy. So there's lots of other forms of energy, such as heat, nuclear, chemical, and so on. But for us in applied maths, we focus on mechanical energy, which is basically potential energy and kinetic energy. We are going to focus on gravitational potential energy in this video, but we do have elastic potential energy, which we meet in Hooke's law, and that's linked in one of our videos below if you want to explore that in more detail. That's more suitable when you study your differential equations. So the energy we're working with here from page 55 of our log tables, you can see we have the gravitational potential energy, which is given as mgh, and kinetic energy, which is a half mv squared. One thing to point out, it's not going to make much of a difference with us here, but it will make a difference when we meet energy with other topics, such as impacts and collisions. Because energy is a scalar quantity, That V is actually speed and not velocity. Now, you might say, does that make a big difference? It will when we get into oblique collisions. Okay, so just bear that in mind. In the same way that height, that H for our gravitational needs to be positive, but that's not usually an issue. The third thing we have here on our page 55 is the principal conservation of energy. So that's basically saying the change, that triangle is delta change. So the change in potential energy plus the change in kinetic energy is equal to zero if, and this is a big if energy is conserved. So there's very specific cases when energy is conserved. It won't always be the case, but if there's no extra forces acting on a system, then that will be true. So let's talk about gravitational potential energy. So near the Earth's surface, the force due to gravity, so its weight of a mass m, is mass times gravity. So then if the body is raised to vertical height h, then the work done is, remember, force times distance, which is the force, weight, mg, times our distance h. So that's where we're getting our potential energy. So that potential energy is equal to the work done. Work and energy are very, very strongly related. Okay, so don't forget that. And that gives us our lovely formula from page 55. So then if we think about kinetic energy, so if a resultant force F moves a body a distance S and speeds it up from rest to V, work can be given as work is equal to force times S, and we can use our equations of motion, so specifically V squared equals U squared plus 2AS, to work out an expression for not just S, we're going to get AS. You can also just get S, but you'll see why we're getting AS here. So remember, U is 0, so body starts at rest, and then that gives us V squared is equal to 2AS. So basically, AS is equal to half V squared. So remember that force is equal to mass times acceleration. So work is equal to mass times acceleration times s. But we know that acceleration times s in the line above is given as a half mv squared. So that gives us work is equal to a half mv squared. So the work done is equal to this kinetic energy, that moving energy. And that's where we get this formula. So you won't be asked to derive either of those energy formulas, but it's a good exercise for you to understand kind of where it comes from. And what I love about this is it really strongly shows us that connection between our work and our energy. So the principle of conservation of mechanical energy. So basically that's saying is if only conservative forces act. So effectively, if a body for us really is just moving under gravity, that's the easiest way for us to think about it, then the total mechanical energy is constant. So basically mgh plus a half mv squared is constant. Usually how we do that is we say, well, the total energy at one position is equal to the total energy in the other. And we're able to utilize that fact to solve some problems. So energy can change form, but in a closed system, it's not lost. So when friction or air resistance come into play, we are going to have a loss in energy. So when we work with our impacts and collisions, you're going to see that we always lose energy. So energy is not always conserved. So that's important, not only to understand when we conserve energy, but also to know when we don't conserve energy. So this will only be the case. Easiest way to think about it, if the only thing happening is something is moving under gravity. That's really for us the only time the conservation of energy is holding true. So another nice addition is called the work energy theorem. So this is the idea of a constant force. So for straight line motion with constant acceleration, and if we start with v squared equals u squared plus 2as, we can then generalize a times s as a half v squared minus u squared. So if we multiply that by m, we're basically getting F equals ma times s, which is effectively work done. So we get work is equal to this half mv squared minus a half mu squared, which is effectively the change in kinetic energy. So work done by a body is equal to the change in its kinetic energy. So when we combine this with potential energy, we actually get then this updated extended really conservation of energy formula. That is the kinetic energy at position 1 plus the potential energy at position 1 plus the net work done should equal the kinetic energy at position 2 plus the potential energy at position 2. So there may be work done that needs to be brought into this situation. This is something we're going to meet at a very, very high level here in this video. We're not doing a huge amount with this. We are going to work a bit more with the idea of work being equal to the change in kinetic energy, but you're going to see this a lot more when we look at Hooke's law in more detail. If you've already completed differential equations and you want to explore this idea in Hooke's law, I've linked the video below. So just a reminder that that triangle is the Greek letter delta and it just means change. So it's a nice way to say the change in kinetic energy. So it is important to understand like, well, when does a force not do any work and why? Because work is kind of a tough one to be asked about because they have to be very clear about what the work they're asking about. Is it the work on the system? Is it work by a specific force? So a force does no work if it's perpendicular to the displacement or if there's no displacement in that direction. So what we mean by that is imagine a block that's sliding along a horizontal table. So we have reaction and weight, but neither of them will do any work because if you can picture those forces, they're perpendicular to the movement. So only forces in line with that movement, so parallel with that movement, are going to do any work. So imagine a block being pulled on a horizontal table at constant speed. Again, nothing is happening here with that reaction or weight. There's no movement up or down. Therefore, they're not going to be doing any work. Now, both the pulling force and the friction are both doing work. They're doing work in like, I don't say opposite direction, but one is doing positive work, one is doing negative work. So what that means for us, because we're working at a constant speed, effectively the net work will be zero. So their work will effectively like cancel each other out. So it's important to note that the pull does work and the friction does work, but because that pull work is positive and the friction work is negative, and the reason we know that is because it's moving at constant speed, there is no acceleration. So that's why the net work is zero because the net force is zero. Because if you think about our formula, work is equal to Fs. If the force is effectively, if the net force is zero, then the net work is also zero. So a car traveling at constant speed on level ground, and again, weight and reaction are there doing no work because there's no vertical displacement. Again, because that tractive force, whatever the engine is doing, pushing it forward, is doing positive work. And then the resistive force, so that's probably air resistance and whatever else, maybe a bit of friction on the tires, that's negative work. So again, that network is zero. So remember, anytime we're dealing with constant speed, we have a net, well, the net force is zero, meaning net work is also zero. So then imagine a stone that's whirled in a horizontal circle on a string. Tension does no work because the force is along the radius. So that's our centripetal force. So if you've studied circular motion already, that's something you're familiar with. The movement is always perpendicular to that radius. So it's tangential is what we'd say. So what that means for us is that effectively tension does no work. Okay. So the tension does no work because the force is always perpendicular to the motion. So this is, I suppose, really trying to highlight that the idea of work and forces, it's not just any force. It has to be a force that makes sense for the movement, that has to be in some way contributing to that movement. So let's start with an example. So a 90 Newton horizontal pull acts on a sledge of mass 12 kg for 25 meters along level snow. The kinetic friction is 18 newtons and the sledge starts from rest. Find A, the work done by each force, and B, the final speed. So when we talk about kinetic friction, we don't distinguish between static and kinetic. There is different friction coefficients. But we don't distinguish between them in our course, so we can think of that just as friction. So the first thing I always suggest we do is a force diagram. So everything in this video is very, very strongly linked to forces. So it's a great starting point. So here is our sledge. It is a mass of 12 kg, and I'm going to put in our direction of movement here. Okay, so we have our 90 newtons, which is pulling it that way, and we have an 18 newtons, which is friction, which is going the opposite way. So remember, friction always opposes motion, which is why that direction of motion is so important for us. So then, if we think about our formula for work, work is equal to Fs, so force times distance. So we're looking the work done by each force. So the pulling force is 90, it's moving at 25 meters. So the pulling force is doing work of 2,250 joules, or you can rewrite that as 2.25 kilojoules. So kilo just means 1,000. So then for the friction force, this work is going to be negative. Okay, it's taking energy out of the system. So that's minus. And then we have 18 by 25, which is giving us minus 450 joules or minus 0.45 kilojoules. So they were asking for the work done by each force. We work those individually. So then for part B, the final speed, we're going to use the idea that the network is equal to the change in kinetic energy. So what we can do here is work with our kinetic energy formula of a half mv squared and simply say that the net work is going to be force. So I'm going to use two ways to show you how to get the net work. So if we hadn't done part A, the easiest way to do it is get the resultant force, which will be 90 minus 18. So 90 is positive because it's moving in the direction of motion, minus your 18, that's your resultant force of 72 times our 25 meters, which is going to give us 1,800 joules. So we can also write that as 1.8 kilojoules. And the other option, because we've done part A, is that we can simply say, well, the pulling force was positive and then the friction force was negative, or sorry, the pulling force was doing positive work and the friction force was doing negative work. Therefore, putting those two together gives us net work of the same. So either option, you may find it easier to do the second option because we've got the individual work done. If you hadn't done part A, then the first option we did there might be better. You're going to get the same answer either way. So now we need to work with the idea that the network, so that 1,800 joules, is equal to the change in kinetic energy. I like that a little symbol for change. That's our delta, but you don't have to use that. You can use the word change if you like. So then our network, which is 1,800, is going to be a half mv2 squared minus a half mv1 squared, where there are different speeds. So our v1 is our initial speed and our v2 is our final speed. So we know that the sledge starts from rest. That gives us V1 as 0, and we're looking for V. We know that it's a 12 kg mass, and then we're just going to work with this. So we get 6v squared is equal to 1800. So that gives us V squared is equal to 300. So V is equal to square root 300. You can leave that in third form or bring it back to decimals, which works out at 17.32 meters per second. So equally here, you could use U and V if you don't want to use V1 and V2. It doesn't matter. We'll get our same answer either way. The big thing here is to understand that the network is equal to the change in kinetic energy. The reason why that's true is because effectively there's nothing else happening here apart from those two forces. So, example 2, A person drags a 50 kg crate 20 meters along level ground by a rope that makes an angle alpha with the horizontal, where tan alpha is equal to 3 over 4. The tension is 150 newtons. Ignore friction. Find the work done by the tension. So, first thing I will always say to do is if you're given something like a tan of alpha equals or a sine or a cos, I would straight away go and do your little dummy triangle and figure out the other two missing ratios. So in this case, sine and cos, because chances are you're going to need to do some resolving, and that's going to be super important. So here's my little dummy triangle with my alpha. Tan is opposite over adjacent, which means I'm going to be able to put in my 3 and my 4 here into my triangle. So if you don't know that this is a special triangle and that the hypotenuse is 5, you can always use Pythagoras to work that out. Hopefully we don't need to, so I'm just going to go straight to my 5 here, and that gives me a sine of 3 over 5 and a cos of 4 over 5. I like to get that done early and out of the way because that's like the easy work. That's the thing we're seeing so much of. So you might as well get that done and dusted so it's there when you need it, because they're not going to give it to you if you're not going to need to do some resolving. The second thing I'm going to do is a nice little diagram, a force diagram to see what's going on. So here's my crate. It's 50 kg. I'm accelerating. I'm saying to the right. It actually really doesn't matter. I tend to move things naturally to the right, but if you move them the other way, as long as everything in your question kind of ties in with that, that's absolutely fine. So we have a rope, but the rope is making an angle alpha with the horizontal. So it looks like this. And the tension in that rope is 150 newtons. It's saying ignore friction. So the only force we have here is that tension force. Now, we need to think about, okay, our movement is horizontal, so we can only deal with forces that are perpendicular and parallel to that movement. So let's resolve that tension into its parallel and perpendicular components. So now we can see I've made a nice little triangle, and our bottom side here is going to be the hypotenuse, 150 times cos alpha newtons, and that works out with my nice 4 over 5 that we've already calculated earlier. We're getting 150 times 4 over 5, and that gives 120 newtons. The perpendicular or vertical component is going to be 150 sine alpha. So remember, we're working that on the basis that the adjacent side is hypotenuse times cos, and the opposite side of the triangle is hypotenuse times sine. So we want to speed up where maybe we once were with slow trigonometry. We want to speed that up now to be able to go straight to writing down each side in terms of sine and cos. So filling that in, that gets us 90 newtons. So I like my force diagrams to be complete. So I am going to put in my weight, and I am going to put in my R, which is my normal reaction. Now, what I haven't done, which you might do automatically, and I would just say be careful with that, the reaction is not equal to 490. And the reason for that is I'm going to actually do out my diagram again so you can see. There's our 50 kg there's our 50 kg mass, and here's our direction of motion. We have our weight acting down, we have reaction working up, but we also have a component of the tension pulling up. And we also have a component of tension pulling it to the right. So you can see now that actually the reaction is only 400 newtons. It's not 490. So just be really, really careful when you're filling things in. I know the reaction and weight are not required for this question, but it's good to kind of keep in good habits anytime you're doing force diagrams. So we're being asked to find the work done by tension, but here's the thing. We have a few different things to think about with tension. So for tension, we have 150 newtons, but we also have a component that's 120 newtons and a component that's 90 newtons. Now, we've already talked earlier in this video how only forces only forces in the direction of movement will do work. So that 90 newtons is not doing work. So if we look at the 150 newtons of tension, that's not all doing work. Only part of that is doing work. So When we're dealing with horizontal movement, only the horizontal component is going to be doing work. So for us, that's going to be 120 times 20 because that's the movement. And that gets us 2,400 joules or 2.4 kilojoules. So a very, very simple little question, but it's very easy to get it wrong. So it's important that you really understand that idea of work, that you're not just looking at that formula going, well, I can sub into that formula. Because it'd be very easy in this question to simply just go 150 times 20, which will be incorrect because part of that force is not doing work, but part of it is. So, example 3, a 4 kg block is pulled 5 meters up a rough incline of 20 degrees by a constant force F along the plane. The coefficient of kinetic friction is 0.15 and the block moves at constant speed. Find F and the work done by the pulling force F, gravity, and friction. So again, we don't distinguish between the idea of static and kinetic friction. Kinetic friction just means as it's moving. So we're going to just treat that as our normal friction coefficient, which is mu. And there is a lot going on in this question, and definitely a diagram is going to be a great way to start. So this is our incline, and we have a mass of 4 kg and we have a 20-degree incline. Now, notice how my arrow, which usually says A, actually says V here. Now, that's because we're moving at constant speed. So you can put in A there if you want, okay? There's nothing wrong with that because the acceleration is equal to 0, but it's moving in the right-hand direction. So really that arrow for us is a direction of movement as opposed to a true acceleration. So it is important that we understand the direction of movement because we might assume that this would slide down. But remember, they told us in the question that it is being pulled up this rough incline. So I'm putting my V there just as a reminder. We have that force that's pulling it up. We know that that force is constant. And then we have weight. We always have weight, which is equal to mg, which we can work out as 39.2 newtons. We have reaction, and that's not equal to anything we know yet. So let's just leave it as or for the minute. And then we have our friction force, which is calculated as mu times or. Now, we do actually need or because we need to understand friction because friction it's parallel to our movement. So it's going to impact on our it's going to impact on our answer. So we're going to need to work out a value for friction. So in order to do that, we need reaction. And in order to work out reaction, we need to resolve our weight. So our weight is the only force that's an issue here. We need to resolve it so that it's parallel and perpendicular to the plane. So we can see here that we make a lovely right angle triangle and our 20 degrees hops up here. So if you want to see more about that, you can look at the video on inclined planes as to why that angle it will always match our incline angle. But we know our weight then can be resolved into 39.2 cos 20, which works out at roughly 36.84 newtons. And here 39.2 sine 20 degrees, which works out about 13.41 newtons. And that means our reaction is going to be equal to the 36.84 newtons that we had for our component of weight that is perpendicular to the plane. So I find it, sorry, and then we work out our friction. So friction is mu times or, our mu is 0.15, our reaction is 36.84, so it gives us friction as 5.53. Now, I find it a little bit easier if I like flip this to be horizontal. You do not need to do this, but if you are struggling with these questions, inclines in general, even in connected particles, if you're struggling with inclines, I strongly recommend that you do this. So this is what our force diagram looks like when I rotate it slightly so that the plane is horizontal. All my forces there are staying the exact same. You can see all my bits. What I have done is I've put in my component of weight here, that 13.41. I find that this, with students who do this, are less likely to forget that component of weight because it's so easy to forget about it when you're doing your work because it's so far away from where the other arrows are. So just be really careful with that. So, first question asks us to find F. Now, remember that we were given V, a constant speed, which means there's no acceleration, which basically means if we were thinking F equals ma, so our resultant force is equal to 0, which effectively means forces to the left equals forces to the right, which means this force, F, will have to balance out the two forces to the left, which means it must be equal to 13.41 plus 5.53, which gives us 18.94 newtons. And that's our answer to part 1. So then for the next 3 parts, it's asking us for the work done. So let's look at them individually. So for work, it is force times distance traveled, so that's 5 meters. So for our pulling force F, that's going to be 18.94 times 5, which works out about 94.7 joules. So gravity, so the work done by gravity, really that's the work done by weight, because we know gravity is not a force. The force due to gravity is weight. So we're looking at the weight component, the weight component that is in the direction of the movement. So we're not dealing with weight, we're not dealing with 39.2, just the component that's it's parallel to our movement. So this is a negative work because it's taking energy out of the system. So that's 13.41 times 5, which works out as minus 67.05 joules. And then our last one is friction. Again, that's going to be a negative work. So it's 5.53 by 5, which gives us minus 27.65. Now, if you want to do a quick check, the net work should be equal to the change in kinetic energy. So remember, we're at constant speed, therefore the change in kinetic energy is 0 because constant speed means the kinetic energy is staying constant. Which means for us, if we add this, if we add the 3 work bits together, it should give us 0. So net work should give me 0. And when we do, it does. So we know that actually this is correct. So don't have to do that, but it's just a nice quick check. And to bring it back to that idea that network is equal to the change in kinetic energy, that is still true for this question. Okay, and our last one to kind of finish up this section on work. So a spaceship of mass 2,500 kilograms increases speed from 500 meters per second to 600 meters per second. Find the work done by its engines. So the easiest way for us to do that is to say network is equal to the change in kinetic energy. So for us, that change in kinetic energy can be easily calculated because we have mass and the two speeds. And that's going to give us network is equal to a half mv2 squared minus a half mv1 squared, where that 500 is our v1 and 600 is our v2. Plugging that into our formula, we get a final answer of 1.375 by 10 to the power of 8 joules. So that's quite a big number. So happy to accept that in scientific notation or standard form. But if you gave it fully, that would be absolutely fine as well. So no force diagram needed in this case because actually we didn't deal with forces at all. We went straight to work. Okay, so let's get back into the idea of energy. We were working with kinetic energy in the last section with work because work is the change in kinetic energy. And now we're going to focus on literally just working with the energy themselves. So this is gravitational potential energy and kinetic energy and the principal conservation of energy. Remember that energy is the ability to do work. Okay, and also remember that energy is a scalar quantity. So unlike work, which was scalar, but we still had like positive work and negative work, for energy, we literally just take it as energy. So example 5, a stone is released from rest at a height h, find its speed just before it hits the ground. So if we use the conservation of energy here, because all that's happening really, it's working under gravity, so its weight is the only force affecting it, we can say, okay, at the very top, it has potential energy, which will be fully converted then into kinetic energy just in that instant before it hits the ground. So the potential energy should be equal to the kinetic energy. What that gives us is mgh is equal to half mv squared. You might think we don't have enough information for that, but interestingly, what happens is those m's will effectively disappear. What that means is it's not important about the mass. So because of the model we use and we ignore air resistance, the mass actually doesn't affect how fast it will hit the ground. We know in real life that may not be true because of air resistance and other things. But for us here now, that's our model that we're happy to work with. So figuring this, that gives us GH is equal to half V squared. So rearranging that, we get V squared is equal to 2GH, or V is equal to root 2GH meters per second. So that's a nice little formula you could then use to find the speed that anything hits the ground. Now, you might be looking at this question saying, well, actually, if I'd seen that question in an exam, I might have gone a completely different way around it. And absolutely, we could. We could use the equations of motion, or another way to say that is our kinematics. So, yeah, if we set that up with the VUAST and we have U, which is rest, 0 meters per second, a is gravity, or 9.8 meters per second squared. I'm saying that as positive because we're dropping it, so it's gravity is helping it, it's accelerating it. Our S is h meters, and effectively we want V. So if we think about our formulas, the best one to use here will be V squared equals U squared plus 2AS. Filling that in, we get V squared is equal to 0 squared plus 2GH. Because I've left the last one in G, I'm going to leave G here, but you could equally put in your 9.8. V squared equals 2GH, or V is equal to square root of 2GH meters per second. So both give us exactly the same answer. So you might say, well, could I use it then if it wasn't released from rest, if it was given speed? So if there was a U? Absolutely. If there was speed given to the stone as it's released, so if it's projected instead of just released or dropped, then we'd have to take into account that it has kinetic energy at that start. So we'd have to account for that. But effectively, again, it will work out the exact same. So let's take a look at example 6. 0.25 kg ball is lifted vertically 1.8 meters from rest and released from rest at that height. Find the work done by the lifter. Okay, so that's an interesting one here. So the body starts from rest, the ball starts from rest, and it's released from rest. So how will we work out that work done by the lifter? Well, we're going to have to deal with this piece here. So we're going to extend this conservation of energy to include our work done and say, well, the kinetic energy at position 1 plus the potential energy at position 1 is going to equal, plus the net work done is going to equal the kinetic energy plus the potential energy at position 2. So the easiest thing I think to do here is to show what this looks like. So let's visualize it. So there's our start height, and we move to a drop height. So that's 1.8 meters apart. So the height we start at, we're going to say is 0. Now you might say, but that's not true. We don't know where it starts. Absolutely. However, and we're going to see this later on in the video, we can take our lowest point as 0, and then the next height up will be just 1.8. We don't have to have actual heights, we can have relative heights. And I will do a question both ways with actual heights versus relative heights, and you'll see in that question that it does not make a difference. What we often see in our questions when we're working with this kinetic and potential energy kind of up and down piece is that often we don't know the absolute heights. We don't know how high each position is. We have to only look at them relative to each other. But relative is enough, okay? We can absolutely work it out with just relative heights. So where I say my start height is 0, you might say, well, we don't know that. But we do know if I take that as 0, then my H2 is 1.8 meters above it. I'm now using relative heights. Our speed there is also 0. So when we basically work with this, there's no kinetic energy, which basically means the potential energy in position 1 plus the network is equal to the potential energy in position 2, which effectively gets us work is equal to the change in potential energy. That's how we are able to work with this. So you can fill out that whole formula and just get rid of those kinetic bits, but effectively there is no kinetic energy at either position. That's the important piece for us to note. So then to get our work, we're going to do mgh2 minus mgh1, And we're going to fill that in with all the information, and that gets us to 4.41 joules. So that's our work done by the lifter. So the work done is basically that added energy into that system to go from having a potential energy of what we're saying is 0 to a potential energy of 4.41 joules. So that's more, I suppose, correct when we talk about those relative heights, because we're really talking about the change in potential energy rather than absolute potential energy. If we want the actual potential energy, we would need to know our absolute heights, but we don't work in that way. We're working instead always with that change in potential energy. So for part B, the speed just before the ball returns to starting level. So now we have position 1 as our drop height and position 2 is where we originally started. It's now moving downwards. It's still 1.8 meters apart. My H1 now is 1.8. My V1 is 0 meters per second because it is released from rest. And we're now trying to find, well, what is that V2? What is our speed when we get to that position? Now, we can just fill into our formula without the work done, because we are only working with kinetic and potential energy here, because that work done was because somebody had lifted the ball from one height to another. There's nobody getting involved here, so we effectively are saying there's no work being done. All we're working with here is kinetic and potential energy. So we're back to a nice, easier conservation of energy question. So when we work that through, we're able to fill into both sides and we get this. So at position 1, we have a half m pi 0 squared plus mgh1. And effectively, that just gives us the potential energy because that's all it has. And then at position 2, we're getting a half mv squared plus mgh2, but h2 is 0. So all we have in the second position is kinetic energy. Tidying that up, we get 4.41 is equal to 0.125 v squared. We can see that that 4.41, we have already worked that out. We already knew that from our part A. But if you didn't spot that, you can absolutely go through all this again. So that gets us V is equal to the square root of 4.41 over 0.125, which gives us 5.94 meters per second. So question 7. At its lowest point, a swing is 0.8 meters above the ground. At its highest, it's 2.3 above the ground. A child sits on the swing. If released from rest at the highest point, find the speed at the lowest point. And then part 2 says, if instead the swing is given a horizontal push, so the speed at the highest point is 2.2 meters per second, find the greatest speed in subsequent motion. So anytime we have a pendulum idea, we're able to use that conservation of energy. So a swing is a pendulum. So what we do is we say a half mu squared plus mgh1 is equal to half mv squared plus mgh2. So again, you can use your V1, V2, or U and V, whichever works best. All we're saying here is U is the initial, V is the final, but that equally could be V1 and V2. So let's take a look at what is happening here. So imagine this, our pendulum. I know I've shown this as a pendulum and not a swing, but the principles are going to be the same. So here's position 1 and here's position 2. So it's released from its highest point to its lowest point. So that means I can say that the half mu squared, so it's kinetic energy at position 1 plus mgh1 plus its potential energy at position 1 is equal to the kinetic and potential at position 2. That is a conservation of energy. Now, easiest way to see this is to draw a horizontal line from the highest point, which creates a lovely right angle triangle. In other examples, we're going to be utilizing that triangle. Here, it's a nice straightforward question with height, so we don't need to. We do need to understand where the ground is. So there is a line to represent our ground, and we know that the highest point is 2.3 meters above the ground, and the lowest point is 0.8 meters above the ground. So that's effectively our H1 and our H2. So we know that the speed given initially is 0 because it's released from rest. So filling in, we get a half m0 squared plus m times gravity times our h1, which is 2.3, is equal to half mv squared plus m gravity 9.8 times our h2, which is 0.8. We don't know the mass, but again, it actually doesn't matter. The mass is not going to affect our final answer. So the mass doesn't actually have any impact. So those m's can be divided out. I'm going to get rid of that piece there. And then we're left with this sum here, which is 9.8 by 2.3 is equal to half v squared plus 9.8 by 0.8. Working that through, we get v squared is equal to 29.4. So v is equal to the square root of that, which works out as 5.42 meters per second. So that's the principal conservation of energy in its really nice basic form in use. So pendulums are somewhere we meet this. Now, I mentioned earlier about the idea of absolute heights versus relative heights. So we've used absolute heights here because that's always given in the question. However, often we don't know that. And because we're only really thinking about those changes in energy, we're never just asked to calculate the energy at position 1 or the energy at position 2. It's absolutely fine for us to work with relative heights. So let me show you how this question would work out the exact same if we used relative heights. So what do I mean by relative heights? I mean, let's assume that this is the lowest point. Now you might say, but we know the ground is lower. The other argument here is, well, actually, because it's on a string, it can't really go any lower. So it's the lowest point in terms of our question, which is enough for us. Now, in this question, why would we not use absolute heights if they're given to us? And yeah, absolutely. But I just want to prove to you that this works out the exact same. So if at the lowest point it is 0.8 above the ground and at the highest it's 2.3, that means that the relative height between these two is 1.5. So I've just got that by saying 2.3 minus 0.8. Now, filling into my formula, just like before, you'll see here that my height for 2 is now subbing in as a 0, which simplifies my sum. The m's are still being able to be divided out, and we get this here, which gives us the same v squared and the exact same v. So actually, it doesn't impact our answer to work with relative heights compared to actual heights. So never be afraid of relative heights, okay? Use them to your advantage. And again, as we work with very hard questions, this can make a big, big difference to us working in a way that's easier. So always work in the easiest way possible for yourself. So part 2 then says, if instead the sling is given a horizontal push, so the speed at the highest point is 2.2, find the greatest speed in subsequent motion. Now, the first thing you might say is, well, it's a horizontal push. Do we need to start resolving? And the answer is no, because if you remember, energy is scalar. So that V represents speed. So it doesn't matter. We're literally just plugging that speed into that formula. So this we're going to work through. I'm going to use the relative height because it just simplifies my sum ever so slightly. And we're getting a half m by 2.2 squared plus m times gravity times 1.5 is equal to half m v squared plus m times 9.8 times 0. I like that because I'm able to just get rid of that term. If I did use the absolute heights, I'd have to kind of deal with that term. It's not a big issue, but I prefer to not deal with it if I can. So here we can just straight away plug in that 2.2. We're not worried about resolving or anything like that because when we deal with energy, energy is a scalar. So it uses speed, not velocity. So let's divide across those m's and then we can get our v squared is equal to 39.24 or 5.85 meters per second. Now, what I didn't deal with when we started this was the idea of find the greatest speed in subsequent motion. Remember that when we're dealing with a pendulum, the biggest speed is going to be at the bottom. And the reasoning for that is because that's when all that potential has been converted into kinetic. So in absolute terms, we think of it as saying, well, the lowest it can possibly be. So that height, the relative height there is 0. So there's relatively no potential energy left to convert. Once it starts moving up the other side, it's going to gain that potential energy, which comes and takes away a bit from kinetic energy. So at that bottom, at that position 2 on our diagram, that's where it has the biggest kinetic energy. And in turn, that's where it'll have its greatest speed. So that's where we're dealing with pendulum motion. Okay, so when it's at its lowest point. So this is the only real exam question that I've put into the video. And the reason is because we're not asked to work on these things on their own. So they have been linked in with other questions. And like I said, I've linked them below. But what I have done here is I've taken an impacts and collisions question and I've edited it slightly to take out the impact part. So if you do want to view impacts and collisions done and you're very happy with this, absolutely go ahead and work through the full unedited version. But this is edited. So what I mean by edited, I have taken out the original part B, which asked about the collision between A and B, and just given the answer for that. So, two small smooth spheres, A of mass 2 kg and B of mass 3 kg, are suspended by light strings from a ceiling as shown. The distance from the ceiling to the center of each sphere is 2 meters. The sphere A is drawn back 60 degrees and released from rest. It collides with B at the lowest point. B then swings upwards, reaching a maximum angle theta with the vertical. Show that A strikes B with speed root 2g meters per second. And then part B, after the collision, sphere B moves off with speed 7 root 2g over 10 meters per second. Find the maximum angle theta that B reaches. So because we're dealing with a pendulum, the swing of both A and B independently can be modeled using the conservation of energy. Okay, so energy is not conserved between A and B, but A conserves energy from its initial position to its final position, in that swing down, and B conserves energy from its first position back up. So we're thinking about conservation of energy individually. So I have taken A out by itself so we can see it, and we want to show that A strikes B with speed root 2g meters per second. So we're going to use that conservation of energy. Here's position 1, here's position 2. So in position 1, we know that the kinetic energy plus the potential must equal the kinetic plus the potential for position 2, and we just need to fill that in. So we know that sphere A is drawn back through 60 degrees and released from rest. Okay, so we know that initially that U is 0. We need to figure out the height, that H1, and we're going to use relative heights here. So our H2 will effectively be 0 because it's the lowest point of the swing, and we're looking for our V. That means we're missing that H1. We're missing the height at A. So this is where we need to actually go a little bit deeper and say, well, how are we going to work that out? So remember that we were told that this string is 2 meters in length. That's important. We're also told that this angle is 60 degrees. What that allows us to do is to use our trigonometry to say that this part here could be rewritten as 2 cos 60 because it's the adjacent side. So that is 1. Now, if that part is 1, then this bottom part to the lowest point must also be 1 because that is still the same string. So the string is 2 meters. So if that top bit is 1, then the bottom bit is also 1, giving us a height here, a position 1 of 1 meter. Now, I know that diagram doesn't show it very well, but your diagram, whatever you're given in the question, it won't tend to. So I know it would say, well, that doesn't look exactly half. That's fine. The diagrams are not drawn to scale. Now let's fill into our conservation of energy formula. That's a half times 2 times 0 squared plus 2g times 1. Remember, we're leaving it in terms of g for this question because we're trying to show that the speed is root 2g meters per second. We can get rid of the zeros, and that leaves us with, so a half times 2 is 1, so v squared is equal to 2g, and that gives us v is equal to root 2g meters per second. So that is our speed as they asked us to do, so QED. So then part B of this says after the collision, sphere B moves off with speed 7 root 2g over 10 meters per second when the maximum angle theta that B reaches. Basically, we want it to be at the very top, which is where it has full potential energy and no kinetic energy. It stopped moving. So We know position 1 and position 2 are here and here. So just be really careful. I do label them as I go because sometimes we're dealing with a pendulum that's swinging from the top to the bottom, sometimes from the bottom to the top. So we know that at position 1, the kinetic plus the potential is equal to the same at position 2. We know that after they collide, we get 7 root 2g over 10, which is our value for u. So let's sub that in. Oh, sorry, we actually can't sub that in yet because I have no height. So we know height 1 is going to be our 0. We know our u. We're looking for our v. And no, sorry, we're not looking for our v because our v is going to be 0 because it's going to stop up there. We're looking for angle theta. So we need to fill in our h2. So we're going to use the same trigonometric idea that we did in the last one, create our triangle. This is 2 meters. So this is 2 cos theta. So then this part down here is going to be 2, the length of the string, minus 2 cos theta. So that gives us our height here. It's not very nice looking, I know, but we're still going to be able to utilize it. So this is what it looks like when we subbed in. Be very careful. We've moved to mass MB, which is 3 kg, unlike the 2 kg we were working with for A. We can get rid of anything with our zeros and we can do a little bit of cleanup here. So I like to leave it in terms of G because we're getting theta. There's no issue subbing G in. If you're unsure how to work with this first piece and you're thinking, oh my God, how would I kind of work that out? You can absolutely put that into your calculator as a half times 3 times the fraction 7 root 2 over 10 all to be squared. Just leave out the G because we have a square root of G that's squared. So that's just going to plug back into our answer as a G. So that's where I got my 1.47. It's pure calculator work. So don't be afraid of using your calculator. It'll speed you up. So you get 1.47 G is equal to 3 by G by 2 is just 6G, and 3 by G by minus 2 cos G is minus 6G. The G's now are all gone, but if you'd sub them in, that's absolutely fine. So we're left with 6 cos theta is equal to 4.53. So cos theta is equal to 4.53 over 6, or 0.755, which gives us final answer of 40.97 degrees. So exact same process to find that angle. So what's really lovely about these questions is you're not thinking about how will I get an angle. You're following the same exact process and you just have different unknowns. So the big piece here to unlocking this question was trying to find that height h and for position 2 in terms of theta. So now let's talk about our final section, which is power. So power is the rate at which a force transfers energy or the rate at which a force does work. So for straight line motion at speed v, the power of a constant force F is given as P equals FV, where F is the force or the component of the force or a resultant of a few forces along the direction of motion. Okay, so this is very, very strongly linked to our work is equal to Fs, P is equal to Fe, but the same idea is there. We have to think in terms of the force along that movement. So there's a second formula for power, which is work per unit time. Which one we use will depend on the information that we're given in the question. So both of these appear on page 55, and you'll see them given as power is equal to work per unit time, or F times V. So that V is technically speed because power is a scalar quantity, and that makes sense if you think of work over time. And it is measured in watts. Now, for dimensional analysis, it's important for us to understand what that is. That's Newton meters per second. Again, I find the easiest way to understand that is to work with P equals FV, F in Newtons, V meters per second. And then just I suppose to be aware, I know we've met it already here, but the idea of a kilowatt, so kilos 1,000. For power, we see this a lot more. And also, you may have heard horsepower, especially in relation to cars. That's about 746 watts. Now, we wouldn't see anything necessarily like that. If we did see it, you'd have to be told that relationship. But just in case you've ever heard it, that we're working the same thing. We're just working in SI units instead of in horsepower, which would be an older unit. So example 8, a cyclist maintains a steady speed of 8 meters per second on level ground. The total resistive force of tires and air is 38 newtons. What power must the cyclist apply at the wheel? So let's do a nice little force diagram. So here is my cyclist. They have a constant speed of 8 meters per second. So I'm using that V instead of my A to make it more helpful. That's showing me the direction of motion, which allows us then to put on that resistive force. So if we have a steady speed, remember that means acceleration is 0, which means our resultant force is 0, or an easier way to think about that, forces left equals forces right. That means there's 38 newtons also being supplied to that right, where that 38 to the left is a resistive force and the 38 to the right is the force supplied by the cyclist. Now we are asked about the power that the cyclist supply, the power that the cyclist must supply at the wheel. So we go to our formulas. We're working with FB because that's the information we've been given. So power is equal to the force supplied by the cyclist, 38 times the steady speed, which is 8, which works out as 304 watts. So example 9, a worker pulls a crate along a smooth floor at a constant speed of 1.2 meters per second using a rope of tension 120 newtons at 30 degrees to the horizontal. Find the power delivered by the worker. So here is our crate and it has a constant speed of 1.2 meters per second. We have our tension at 120 newtons, but it's at 30 degrees to the horizontal. So first thing we need to understand is any forces need to be in the direction, well, either parallel or perpendicular to what we usually say acceleration, but direction of motion. So I'm going to need to resolve that tension into its horizontal and vertical components. So this works out as 120 cos 30 or 60 root 3 newtons. And here is 120 sine 30, which is 60 newtons. So we also have this idea of a weight and a reaction. I like my force diagrams to be complete if we're kind of doing any more with them. So here for our V, we can see that we have our weight, our reaction, but we also have a component, the tension pulling it up, and we have our 60 root 3, that component of our tension pulling it to the right. So that's our completed force diagram. We are being asked for the power delivered by the worker. Now, it'd be very easy to say, okay, that's 120 times 1.2. However, since the motion is horizontal, the power is given only by the component that moves in that direction, meaning the power delivered by the worker is only going to be 60 root 3 by 1.2. So because it's at an angle, that's like wasted power effectively. So, or wasted force. So part of that force is not being included. So this works out as 124.71 watts. So, example 10, a small winch hauls a 40 kg load up a rough ramp of angle 20 degrees at constant speed 0.8 meters per second. The coefficient of kinetic friction between load and ramp is 0.15. Find the winch power. So first thing I say is, oh, what's a winch? So a winch is basically a machine. I'm sure you've seen it, and they're used to pull or lift something quite heavy, and it uses a cable that's wrapped around a rotating drum. So that black drum is turning and either releasing that cable, it's not really rope, cable, or pulling that cable back. So you might see it on like a tow truck or a crane or a boat, or even lifts use this idea. So what does it really mean for us? Because that's really all we care about, isn't it? So in applied maths terms, what does it mean? So basically it'll have a tension. That's it. It's a rope with a tension. That's basically all we need to know about that idea of a winch. I know sometimes when we meet words like this, it can really throw students, which is why I just wanted to make it very clear what we were dealing with. So let's draw our force diagram. So we're at a rough ramp and it's at 20 degrees. So I have a constant speed of 0.8 meters per second. We're pulling up the ramp. So there's our 40 kg. Here's our 20 degrees. Now you might go, that's a lot more than 20 degrees. The bigger you make that angle of your drawing, the easier it is to do your resolving. So make sure your diagram is big enough and gives you enough space to resolve. So we then have our weight, which is equal to mass times gravity, which works out as 392. We have a reaction and we have a friction, which is mu times R. So our friction, it's really important that we understand direction of motion so our friction goes in the right way. So we need our reaction to calculate our friction. So we're going to need to resolve our weight. So our weight can be resolved into the horizontal, really parallel and perpendicular components. And we get 392 cos 20, which works out about 368.36 newtons, and 392 sine 20, which works out 134.07 newtons. So our reaction there is 368.36 newtons. So our friction is 0.15. That's our coefficient of friction, mu, times our reaction, 368.36, which works out as 55.254 newtons. Again, I like to have these horizontal, so I've rotated everything. So they're asking us to find the power of that winch. But actually, first of all, we need to figure out, well, what's the tension? Because we need that force to get the power. So remember that we have constant speed, which means there is no acceleration, which effectively for us means forces left equals forces right. So that means that T, that tension, can be given as 134.07 plus 55.254, which works out 189.342. And now we can work out our power as F, that force, times velocity. This is just the power of the winch itself. So we're using the force of the winch times that constant speed. And that works out as 151.4592 watts. Okay, so example 11. A 900 kg car has a constant engine power at the wheels of 60 kilowatts. On level ground, the resistive force is R equals kV squared, where K is 5.3 Newton second squared per meter squared. Find the maximum steady speed on level ground. So, before I do my force diagram, I need to have some forces. So I was given the engine power. So I'm going to convert my power back to a force. Now, this is something we see quite a bit when we deal with differential equations and when we're setting up our differential equations, because we're able to deal with scenarios where that V is varying, not just steady speeds. When we have a speed that's varying, we need to work with differential equations. So if you've got differential equations done and you want to check this idea out and how we apply it to there, I've linked the video below. So I'm going to convert that power to a force. So we have P is equal to FV. So then F, the force, is power divided by velocity. So we don't know what that V is. We're trying to actually find it. It's the maximum steady speed on level ground. So now I'm going to draw out, I'm going to plug in my P first. So my 60 kilowatts is 60,000 all over V. And now I'm going to draw out my force diagram. So I start with my car. My direction of movement, I'm saying, is to the right, and that's V. We don't know what V is. That's what we're going to work out. We know that we have a resistive force to the left, which is kV squared, where K is 5.3. So that's 5.3 V squared. And then we have a force applied by the engine, which we've worked out as 60,000 over V. Now, because we're dealing with this idea of steady speed, we know there's no acceleration, which basically means forces to the left must equal forces to the right, which basically gives us 5.3 V squared is equal to 60,000 over V. And rearranging that, so I get, multiply both sides by V, I get 5.3 V cubed equals 60,000. So V cubed is equal to 6,000 divided by 5.3. And that works out as 22.45 meters per second. So I think going back to your force diagrams will always help you kind of make better sense of these questions. And it's unlikely we see something like this where it is a constant speed. It's more likely to come up in the sense of that v being a variable. And like I said, I've linked that video below. So our last example, example 12, a builder raises a 2.5 kg bucket vertically 12 meters in 10 seconds. Find the average power output. Now, few things that are going on here. Because the question is asking us average power, we can assume that that bucket is raised at a constant rate. Okay, so we're looking for that average power. So we can think of it as having an average speed. So we're going to work with that average speed instead of a changing velocity. Okay, so our average speed. So here is my 2.5 kg bucket. It's being raised vertically at this constant speed. I have a weight that's pulling it down, which is 2.5 by 9.8, which works out about 24.5. There is then a tension force, or they don't tell us what the builder is doing. Maybe it's a pulling force. I'm just going to call it tension. But you could equally just call it a pulling force. We don't know how he's raising it, but he is applying some force to that. Now, if we've no acceleration, because we're assuming that there's no acceleration, that that's constant speed, we now can say, well, actually that tension must equal that weight. Okay, so that's an important kind of idea to get us moving in the right direction. So remember, we're trying to find the average power output. So the power is work per unit time. And because we don't know what that V is, so we're going to use the formula work per unit time because they did give us time. So we're going to figure out, first of all, the work done. So our work is force times displacement, so Fs, which basically gives us 24.5 by 12, which gives us 294 joules. And then we can find the power output. So that is going to be 294 over 10, and that gives us 29.4 watts as our average power output. But we have made some assumptions to come up with that answer.